The role of any bioinformatician really is the acquisition of data, the engineering of that data, perhaps reconfiguration and processing, and then deploying mathematical models using computational systems to extract information, to discern patterns, and to build models which we can then use to learn how biology behaves.
I find it a really interesting job to do. I will have some days or weeks where I'm really just writing a lot of code. And then as the project goes on, you'll be kind of maybe trying to make things more efficient so that you can analyse a lot of samples and then go through to kind of trying to bring out the story from the data.
So my typical day-to-day, I guess, depends on what part of the project I'm in. So at the beginning of a project, it might be chaining together different tools and pipelines. If I'm in the sort of middle of a project, then it involves applying different sort of statistical techniques to the data. And then at the end of a project, it's usually making sure that the data is well documented, it's in an open access repository to be able to share with other researchers.
My favourite part of the process really is visualising the data. So we're often working with data that's very highly dimensional, so you have to do some kind of mathematical techniques to make this really, really complicated data set something that you can look at on a diagram, presenting that in a way that you can help other people understand what you do.
We have a saying in the machine learning and computational world that if you put trash in, you get trash out. And so I would say the biggest challenge for all of us is sort of really understanding the data you're working with to do proper quality control and filter things so that you can trust that when you run your methods on it, you can trust the results that come out.
Working with bioinformaticians, I think, is a relatively easy process. Probably one of the best things to do is approach with a good understanding of your data. And you don't even necessarily need to know what it is that you want to achieve. We're quite happy to do exploratory data analysis and have a look at the data and perhaps inform the questions that you didn't know needed to be asked.
Things like the biobank are really useful because when you have 500,000 people, it's really likely that you've captured almost all of the genetic variation that you can. But because of the size and scale, you really need incredible computational power and methods to access those.
We're able to compare our data with data of labs from all around the world in a really fast and efficient way. Once we've started to build up these large repositories of data, we can build computational models to extrapolate what might happen in different health states to improve health outcomes.
I would say computational biology is quite different to wet lab. So in the wet lab, you're quite used to following protocols. You know where you're trying to get, you have your controls, you know what it should look like at the end. Whereas in computation, every single step along the way, you're not really sure what you're getting out, and there's a lot more parameters and tuning that has to go on. Every single step you're optimizing.
One thing people wouldn't necessarily realise is how long the analysis can take, because on the face of it, it can seem quite straightforward, and the actual reality is that, if you're going to analyse a large data set, it can take months or even years. The work I'm about to publish, I've had that data for about 2 years.
Often bioinformatics is a great place to start, not necessarily just a place to end up. So I think that that's one of the misconceptions that we're often given, is that we do the data analysis after the majority of the investigation's been done, but actually I think it's a really good place to start your analysis.
As long as you're open to learning a lot about the new domain that you're entering, I think it's a really exciting time to be a computational scientist, because you can start to bring value very quickly to whatever domain you want to be in.
So I think there's lots of really exciting developments. I think the amount of data that's being generated now, and I think the ability to sort of link things like electronic health records to genomic data and being able to test them is really exciting.
I think that leveraging technology and the way that it moves forward so rapidly for biological research is absolutely critical. And that's exactly what we're able to do here in the computational biology suite, is take the rapid advances in technology, apply them to our research, combine them with research from around the world, and speed up the process so that ultimately we can help more people faster.